All right, so we're now gonna look into numeric literals. Numeric literals. The word literal, for some reason, it throws me off because we do know. Okay, let's see what the word literal mean. Taking words in their usual or most basic sense without metaphor or exaggeration. Literal. Okay, I guess what that means. I just understand what that means. Things as they really are. That's pretty much what it means. Numeric literals. What do we learn about this? Okay, let's see. Integer literals can be written as decimal number with no prefix. Okay, a binary number with a 0b prefix, an octal number with 0. Okay, well, I understand what this means, decimal number with no prefix. Okay, I see what that means. So then binary number, it has to have a prefix of this to indicate that this is a primary. What is this? This is a binary number. So the 0b here, I guess the B stands for binary. An octal number, which is a 0, I guess the 0 I guess the O here means it's an octal. A hexadecimal number with a 0x prefix. I guess the X there stands for hexadecimal. All these integer literals have a decimal value of 17. Okay, we see what that means. Okay, cool, I see that. So let's say, I guess I understand what it means. Let's say you have a binary number and then you want to store it here. You can store it. Okay, let's try to test this and see how it's gonna display in here. Or how it's gonna print. I'll say here numeric literals. Okay, I'll look into that. So we have let. Okay, well, if it's a let, let me do a var. Okay, well, it's the same thing pretty much. Let decimal integer is equal to 17. That's fine. Let binary integer is equal to 0b. Okay, now it recognizes it as a binary number. Okay, cool. So now let me print this. Print binary. Can't see now what I say with this. Print binary integer. Okay, obviously it's gonna save it as 17. Interesting. So, okay, well, that makes sense. It won't save it, but then can we convert it back to a binary integer? I mean, to a binary value. How would we do that, though? Let me see. I don't know if the word binary exists here. Oh, it's not a function, so it doesn't exist. So we know double exists. We can typecast it to a double, but then I guess for binary, which makes sense. I mean, because how would we display it? Are we gonna display the 0? Interesting point. Let's see if we're gonna display this. What's gonna happen? Cool. Okay, it displays it as 17 as well. So which means the compiler converts this back to an integer and then it displays it, which is fair. I see what it does there, which is fair, because now the moment that I introduce a b, it now becomes a string and it's no longer a number. But then obviously because we put this prefix here, the value is recognized by the compiler as a binary number. So let's do x. I doubt this is gonna work. An octal value. Ooh, it's a lot number. Okay, let's do an O here. All right, cool. Anyway, so we see how it works. But then pretty much what this does is that it converts it first into an integer before it prints it out. So let's see. Floating point literals can be decimal with no prefix or hexadecimal with a prefix with a 0x prefix. They must always have a number or hexadecimal number on both sides of the decimal point. Okay, I see what that means. Wait. Decimal floats can also have an optional exponent indicated by an upper or lowercase exponent. Hexadecimal floats must have an exponent. Indicated by an uppercase or lowercase. Cool. Lowercase p. Okay. For decimal numbers with an exponent of the base number is multiplied by 10 to the power exponent. Okay, I see what that means. Okay, I see what that means. For hexadecimal numbers with an exponent of the base number is multiplied by 2 to the power exponent. So 0xf p 2. So the p there, the lowercase p, well, it makes sense why it's a lowercase p, but then also we know, I'm not sure, I don't think hexadecimal numbers ever reach a p. I think they end with an f, which is a, b, c, d, e, f. I think I'm sure it ends with an f. I could be wrong. All these floating point literals have a decimal value 12.1875. Okay. Numeric literals can contain extra formatting to make them easier to read. Both integers and floats can be padded with extra zeros and can contain underscores to help with readability. Another type of formatting affects the underlying value of the literal. Okay. Okay, so let's see here. Numeric literals. I don't know if I read this. Another types of, okay, well, I read that. What is that underscore there? Literals, okay. Okay, let's see. Numeric literals can contain extra formatting to make it easier, okay, to read. Okay, I guess what that means. For example, if we want to store 1 million, we can add underscores so that we can help us read them better. Both integers and floats can be padded with extra zeros and can contain underscores to help with readability. It makes sense why at one point when we were trying to create a very long number, I only inserted zeros only, and then guess what? It saved the number as a 0. So the extra zero padding, I guess it does nothing really. That's why we can have thousands of them. They will do nothing. Another type of formatting affects the underlying value of the literal, which makes sense. I guess that's what we came to learn even about. What is this? What was this? But I find this interesting though. Whenever they talk about literals, they use the keyword let, but it appears that they've always been using the word let, and we understand let is a constant. Var, they used it here, but then that's naming constants and variables. Anyway, it's fine. I guess they prefer to use the word let. They prefer to make them constants instead. So yeah, we're gonna end it here. This is one of the most interesting things here, how we can add these underscores to help us read the values. So we're gonna end it here. I think I'm recording here. Okay, cheers, guys.